April 6, Physics 112. Okay, this is going to get complicated, but we'll go through it careful step by careful step, because we're going to start modeling parts of the behavior of the action potential by adding resistors to make the model circuit more complicated. So, as we were shown by one of the groups, if you look at the action potential, this is the voltage inside the neuron, outside is 0. Time is passing. You have the resting potential, which we've already established is a negative 70 millivolts. In the action potential, a signal is propagated down the neuron and it causes channels to open, and changing voltages cause channels to open and close, and other channels to open and close. And we're going to model that with switches. But there is a point at which the more sodium channels open. That's supposed to look red. Wow, okay. And at that point, the potential shoots up. You have what they refer to as depolarization. Which is a little bit of a misnomer, because polarization, remember, is a separation between plus and negative. In this case, the inside of the cell is negative. What happens is you don't simply have both sides, inside and outside, equally charged, but it switches around, so now the inside is positive. And it goes up until we reach a potential of plus 40 millivolts. Okay, so I have not drawn this on a very good scale. This should be bigger. This should be smaller. The basic idea is the inside of the scale switches from being negative 70 to plus 40 millivolts. Okay, then something else happens, and we'll get to that. Let's deal with one thing at a time here. So, how do we model this idea of sodium channels, extra sodium channels opening up? Remember what our basic model of the circuit was. The sodium potential, because of the diffusion of sodium ions and the charge that creates, makes the inside a little positive. And there's a resistor which models that the membrane is less permeable. We'll use 716 ohms. This is the sodium. This is outside. This is inside. Over here we have the potassium. Its model resistor was 100 ohms. We did the calculations. What matters is the ratio of these two. It's 7 times harder for the sodium to get through than for the potassium. And we connect this to make a circuit. The potassium, because there tends to be more of it inside, tends to diffuse outside, tending to leave the inside negative to the tune of 89 millivolts. It's negative. We don't write the negative sign here because the fact that this is making the inside more negative is indicated by the short bar here, which is the negative part. So that's the circuit we had before, and this is the circuit that led to the voltage inside, treating the voltage outside as 0, because we get to pick where 0 is. Then with this circuit, the voltage inside was the negative 70 millivolts. So to model what happens when sodium channels open, we'll add a resistor. This resistor will provide an alternate path. I'll put a switch here, and when I close the switch, that will indicate the opening of the path. And I'll put the other end here. So it will provide an alternate path for sodium ions. We don't know what this resistor is yet. We'll call it R. When this switch closes, it's equivalent to opening sodium channels. So we open sodium channels. That's modeled by closing the switch. Which means we are adding the resistor R as an alternate path, or in parallel, to the existing path, which was 716 ohms. So it provides an alternate or parallel path. Okay. So, you might say, what is this value of R? In other words, when these channels open, in a sense, how much extra permeability do they give? What's their resistance compared to the existing resistance? We can figure that out simply by knowing that in the action potential we go up to plus 40 millivolts. We can figure out what this resistor would be in this model circuit, and that therefore gives us the relative permeability of the new sodium channels compared to the previous sodium channels, and the new sodium channels compared to the existing potassium channels. Later we can do the same thing for potassium and see how easily potassium can get through when new channels are opened up. Okay, so here we go. You ready? So we close a switch. What's going to happen? Well, let's look at one side at a time. So the side that is the sodium, I'll redraw it over here. Again, it is modeled with a 66 millivolt battery, with the negative, the outside, and the positive towards the inside. And when the new channels are open during the action potential, we now have two resistors in series. The existing 716 ohms that was there during the resting membrane potential, and now this unknown resistor R, which corresponds to these new channels that have opened. And then this goes off to the potassium side of things, which at the moment is unchanged. So we still have the 89 millivolts. The negative part goes inside the cell, and we still just have the 100 ohm resistor. Okay, so again, over here we have sodium. Over here we have the potassium. And we are artificially making a complete circuit here for purposes of our model. Okay, what do we want to know? We want to know R. Do we know anything about what's going on with R? Well, actually we do. Because we know during the peak of the action potential, so when all the channels are open and everything's going full steam, that the inside of the cell is plus 40 millivolts. So now, instead of being negative 70 millivolts, all of this is plus 40 millivolts. The outside is still 0. That's our reference point. Now, when you're watching voltages, you can go through a particular path and see what's going on. So, for instance, going from here to here, I go up by 66 millivolts. Going from here to here, if we treat the current, so there's some total current coming in here, and we've seen before it's going to split into two separate currents. Let's call them I1 and I2 for now, and we know that that total is I1 plus I2. That's the junction rule. You know, whatever's happening here, whatever current is flowing here, we know that in the end we have 40. So we go from 0 to plus 66 and then down to 40. Writing it in terms of potentials, we end up with 40. We start here at 0. We increase by 66 when we go from the negative to the positive of the battery. And then, since we're going in the direction of current, this is a drop. The energy lowers, and we can see that because we end up at 40 millivolts. That's a drop. And by Ohm's rule, Ohm's law, that's equal to the current through that leftmost resistor times its resistance, 716 ohms. And by the same token, we can follow this path. We get the same result. We end up at 40 millivolts. We started at 0. We go up 66. And we drop by an amount equal to the current through that rightmost resistor times its resistance. And that resistance is what we're trying to figure out. Well, there are some things we don't know yet. We don't know I2, the current through that resistor. We could figure it out if we knew I1 and the total current. But if you look here, here's an equation where I1 appears, and it's the only unknown thing. So we can figure out I1. We can figure out the current that's going through this leftmost resistor. And with what we did previously, we know how to figure out the current going through this loop. In fact, we don't even need to do the whole loop, as we'll see, because that total current, if we follow the junction rule all the way around, the rule for series, all of this is in series, that total current is the same current that's going through there. Well, what does that mean? Well, if I start here, where I'm at 40 millivolts, I go through this resistor in the direction of current, water flows downhill, so that's a decrease of potential equal to the current times the value of that resistor. Then I go up, this pumps the energy up, I'm going from negative to positive of the battery, so that's an increase, 89 millivolts. And when I do all that, I end up at 0 because outside is 0. This equation, the only thing I don't know is IT. So I can use this equation to figure out the total current going around the circuit. I can use this equation to figure out the current going through the 716 ohm resistor. Then that will let me use this equation to figure out the current through the rightmost unknown resistor. And then finally, I will have the information I need to figure out the resistor. Okay, stop here for a second. Make sure you understand each little piece of this. This piece, I went from outside to inside through the 716 resistor. And it's using what happens when you follow a path to the voltages. They add up. This one, going from outside to inside through the unknown resistor. And this one, I'm going from inside to outside through the potassium. Okay, now there's algebra here, but fortunately it's not the do lots of substitution and combining things algebra, but if you take things one step at a time, work with an equation where there's only one thing you don't know, figure that out. There's actually two of those equations where there's only one thing you don't know. This one contains a total current. This one contains a current through the 716 ohm resistor, so you can figure out these two currents. Then we can figure out I2, and that will leave only R unknown here. Go ahead and give it a try. You'll get more practice with this again when we deal with the potassium channel. But go ahead and give it a try before you see what I do. Okay, let's go. So first, let's see if this blue pen will show up blue this time. Good enough. Okay, so we can start with this one first. Okay, what do we want to figure out from there? We want to figure out the total current going around the loop circuit. Okay, do some algebra. We can move these voltages that are numbers to the other side, subtract these numbers from both sides. So we'll have minus IT times 100 ohm resistor equals, and when I subtract this from both sides, I get a negative 129 millivolts. Okay. Divide by the 100 ohms and multiply both sides by a negative. I will have IT equals 129 millivolts divided by 100 ohms. And an ohm, remember, is a volt per amp. And I get 1.29 milliamps. That's the total current going through the circuit. Some of that current will go through here. Some of that current will go through here. I need to know this current to figure out the resistor. But to get this, I just got the total current. So now I need this current. Okay, so we'll work with this equation now. Okay, so what do I have? We can subtract the 66 millivolts from both sides. 40 minus 66 would be minus 26 millivolts. And remaining over here, we'll have minus the current through the 716 ohm resistor times that resistor. And I can multiply both sides by a minus sign. This is just saying that that resistor is changing the voltage. This is basically Ohm's law for that resistor. So I can divide by the 716 ohms. I1 will equal 26 millivolts divided by 716. An ohm is a volt per amp. This is a 7. And what do we get? Let me just double check this calculation. So 26, 716, and yep, 0.0363. Milliamps, because the volts cancel and 1 over amps on the bottom flips over on the top. That's pretty small. I mean, you can see right here, look at this. Almost 1.3 milliamps, but only about 0.04 of it is going through this resistor. The rest of it is going through here. So we get a lot of current here, a little current here. That's telling you something about how easily it is for the ions to go through here. It must be a lot easier to go through here. Okay, well, now we can do that last calculation. And we'll start that on the next page. Okay, so the remaining equation we have to work with, I will recopy it. We get 40 millivolts on the inside, and we get that by starting outside at 0, going from negative to positive of the sodium battery, and then going in the direction of the current of the unknown resistor. Well, we need to know I2 still, but we know that IT equals I1 plus I2, so I2 equals IT minus I1. Total current is 1.29 milliamps. And the current through 1 was 0.0363 milliamps. And I get 1.25 milliamps. Okay, so up here, I want to know what R is. I'm going to subtract the 66 millivolts from both sides, so this will be a negative 26 on the left. That will equal a negative of the current I2, 1.25 milliamps times the unknown resistor. So the unknown resistor will be 2.6 millivolts divided by 1.25 milliamps. That should not be 2.6 millivolts, that should be 26 millivolts. And I basically get 20.7 ohms. So in comparison to the other resistor of 716, this is a factor of 34.5, so about 35. In other words, when the sodium channels open up during the action potential, the new channels are roughly 35 times more permeable than what was already there. And we figured that out simply by modeling it as a circuit using the resistors we had before and knowing what the peak potential of the action potential is. Okay, it would be good to have a way of checking this because it's pretty complicated. Okay, one thing about resistors in series, parallel, we have R1 and R2, a total current coming in, of which I1 goes through the one resistor, and I2 goes through the other resistor. And this is happening with a potential difference, delta V, between the ends of the resistor. And it's the same for both because they're in parallel. So then if we take Ohm's law, which says current equals delta V over R, then the total current, which is the sum of the separate currents, is equal to the delta V over the first resistor plus delta V over the second resistor. And we can say that the same result would happen if we put an equivalent resistor, one equivalent resistor, across the same potential, that we would get the same total current. This is a way that sometimes helps you simplify circuits. Same total current, same delta V. So by Ohm's law, that would be delta V divided by whatever this single equivalent resistor is. Do a little algebra. In the equivalent resistor for a parallel circuit, you take the inverses of the separate resistors, add that up, take the inverse of that. Essentially what you're saying is that the total conductance equals adding up the separate conductances, which makes sense. It's kind of like the continuity equation. You have certain conductance coming in, that's the sum of the conductances coming out. What's coming in equals what's coming out. So we can use that as a quick check on what we've done. For the circuit consisting of the parallels, we know that the voltage across here is 26 volts. 66 here, end up at 40. So the total voltage is 26 volts. Not worrying about the sign here because we're just using Ohm's law to get sizes of things. That equals the current, the total current coming in, which was 1.29 milliamps, times the equivalent circuit equivalent resistance of the entire sodium channel, not just the original one plus the new one, but the whole one altogether. So the equivalent resistance of the sodium channels would be 26 millivolts divided by 1.29 milliamps. The millis cancel, volt per amp is ohms. 26 divided by 1.29 is 20.2 ohms. If all this is consistent, I should get the same answer if I take the original 716 ohms, take the inverse to get the conductance, take the inverse of what we just found, the 20.7 ohms, the conductance through the newly opened channels, add those up, take the inverse of that, that should give me also the equivalent resistance. Okay, so if I take the inverse of 716, I get 1.4 times 10 to the minus 3, that's 1 over ohms. Take the inverse of 20.7, I get 4.83 times 10 to the minus 2, inverse ohms, add those together and take the inverse. And I get 20.1 ohms. Within rounding. I've been keeping 3 digits here. A little suspect, but that's the digit I might expect a little rounding error to come in. You'll notice that this equivalent resistance of the complete set of channels is pretty close to the resistance of the newly opened channels by themselves. When you have a big resistor, 716 ohms, in parallel with a much smaller one, 20.7, the smaller one is going to really dominate what's going on. And you'll see that this is in fact even smaller than that. So you have less resistance for the total than you do for each one separately. Okay, that was complex. For practice, try doing the same thing for the potassium channel. So after the peak of the action potential, it comes back down again and actually overshoots. And the level it reaches is negative 90 millivolts. Okay, this is called the repolarization. Basically, still polarized. It was always polarized, but now it's going back to what it was. And basically, the sodium closes and the potassium opens. And it comes all the way back down here with the potassium open. What will our model look like? This represents the outside. Over here, the potassium channels have closed. So we will simply have, the sodium, so we simply have the sodium we had before. The 66 millivolt battery with the positive going towards the inside of the cell. With the 716 ohm resistor in series, representing that the membrane is less relatively permeable. Okay, so this is sodium on this side of things. On this side of things, we'll have the potassium. So we will have the 89 millivolt battery, representing all the processes that are separating the potassiums normally during the resting situation. We will have the normal 100 ohms, representing how permeable the membrane is to potassium during the resting. Then, during the action potential, I'll just go ahead and close this switch. We will have another resistor. Question is, what is this resistor? How permeable does a membrane become to the potassium as a result of these extra potassium channels opening during the action potential? Yes, it's a little complicated. There are a lot of steps. But try to break it down and take it piece by piece. You have a total current. Coming through here. You have separate currents coming through here and here. You know the potential inside because you know that it is negative 90 millivolts. And again, the outside is always 0. So you know you drop 90 millivolts going through from here to here. That will tell you something about this current. You know you drop 90 millivolts going from here to here, through here. That gives you a relation. You know you drop by 90 volts going from here to here. That gives you a relation, which will let you figure out the total current. And then you can work back, figure out the current through here. And then knowing this voltage, I'll let you think about that. You can figure out the current. Figure out the resistance. Okay, so give that a shot. Take some time with it. I'm not just going to write the solution, put it on Moodle. I will actually go through it carefully next time. Go through the process of the equations and checking it. Then there will be another thing we will have to figure out. Why this goes back up to negative 70? Well, that is simply because at that point everything closes again. All of the extra channels are closed. The only thing open are the original channels. But we will have to think about why these are nice smooth curves, and these changes don't happen suddenly when we open and close the switches. Because this transition takes a little time. This transition takes a little time. I haven't put those times on here, but they're there. We'll have to discuss another feature of the model to explain that. Before we do that, though, we'll probably do a little more practice with these equations in a couple other contexts, using series parallel circuits and Ohm's law and a couple other situations. a couple other conceptual things to look at too. Okay, so next time we'll go through this. Then we'll look at some other situations. Then we'll look at, well, why don't the voltages simply change suddenly instead of taking time to change? That'll be all for now.